The Poisson distribution is a probability distribution for an event occurring x times over a given interval. The probability of that event occurring x times over a given interval is given by the formula e to negative lambda multiplied by lambda to the x divided by the lambda factorial. So P of capital X equal to X, once again, is equal to e to the negative lambda multiplied by lambda to the x divided by x factorial. An example: the manager of a bank determined that an average of 9.2 customers use a certain ATM machine every hour. 9.2, the average is lambda, and when we apply the formula, we get P of 5 customers is 5.5. Let's check the answer with the calculator. We open up the parenthesis. We look for second function ln, which is e, and e to the negative lambda minus 9.2 times lambda, which is 9.2, to the x, which is 5. Exponent 5. And we close the parenthesis and we divide the whole thing by 5. 5. And then we look for the factorial, math, probability, and then down to 4, enter. Now we could just click enter and we get our answer, 5.5%. Number of patients who arrive at an emergency room between 6 and 7. Number of phone calls per day at a switchboard. These are examples of events that can be modeled upon a Poisson distribution. Remember that the x is discrete, therefore x will have an integer value. According to the records, the number of patients arriving between 6 and 7 can be modeled upon a Poisson distribution with the average lambda equal to 6.9. We need to determine the probability that exactly 5 patients arrive between 6 and 7. So lambda is equal to 6.9, and x in this particular case is equal to 4. And we just want P of capital X equal to 4. Now, we're just going to substitute the different values into the formula. P of capital X equal to 4 will be equal to e to the negative 6.9 multiplied by 6.9 to the 4th divided by 4 factorial. P to the capital X equal to 4 will be equal to, well, let's use the calculator, parenthesis, e to the negative 6.9 times 6.9 to the 4th divided by 4 factorial, enter 4, then math, then scroll over to probability, scroll down to factorial, and our answer is 9.5%. 9.5% is the probability that 4 patients, exactly 4 patients, will arrive to the ER. between 6 and 7 p.m. Now, let's look at the second question, B. At most 2. Well, at most 2 means 0 patient, 1 patient, 2 patients. As an inequality, it means that P of capital X is less than or equal to 2. So P of capital X less than or equal to 2 will be equal to P of capital X equal to 0 plus P of capital X equal to 1 plus P of capital X equal to 2. P of capital X equal to 0 will be e to the negative 6.9 times 6.9 to the 0 over 0 factorial plus e to the negative 6.9 times 6.9 to the first over 1 factorial plus e to the negative 6.9 times 6.9 to the second divided by 2 factorial. E to the negative 6.9 is a common factor. 6.9 to the 0 is 1 over factorial 0 factorial, which is also 1, plus 6.9 to the first is 6.9 over 1, so it's 6.9, plus 6.9 squared over 2, and the decimal value is 23.805. And the answer is approximately, we're gonna have e to the second function ln e to the negative 6.9 multiplied by open up parenthesis 1 plus 6.9 plus 23.805, and the answer is 0.032 approximately. So it's 3.2%. C, between 4 and 10 inclusive. The patients have to be between 4 and 10 inclusive. So P of capital X between 4 and 10 inclusive means largely between 4 and 10. We'll have P of capital X equal to 4 first, then plus P of capital X equal to 5, plus that P of capital X equal to 10. So it's 5, 6, 7, 8, 9, 10. Once again, we'll factor out e to the negative 6.9, and we're going to be left with 6.9 to the 4th over 4 factorial plus 6.9 to the 5th over 5 factorial plus that plus 6.9 to the 10th divided by 10 factorial. According to our calculator, the answer will be 0.821. For the next 3 questions, they need the table of probabilities for the random variable x. Now, that table has to be continued until the probability becomes 0 to 3 decimal places. Remember that you will have to stop when the probabilities become 0 to 3 decimal places. After the 8 attempts, the probability became 0.000 according to your book. Now, the partial probability histogram of the random variable x is right skewed, and here's a picture of it.